morning everyone, and welcome to today's worked exam answer video. Today I am again looking at a question that technically could be from either an AS or an A-level paper, AQA specification. I'm having a look at a structure and bonding question, which also links into the reactions of chlorine from the Group 7 inorganic topic. And I've chosen this question because there are a couple of equations that we need to have learned to be able to answer part B and C. So it's important for me to make sure you're aware that those are equations you need to learn. But perhaps most importantly, I've chosen it for part A because we're going to have to explain the origin of van der Waals intermolecular forces, and that can be very tricky in terms of, I'm sure you know sort of what they are, but it's how do we get that in words and communicate and articulate it using the right terminology. So part A is my main focus, but we do also need to know the equations that I'm going to give in part B and C as well. Okay, so this whole question is about chlorine. Now, first of all, it doesn't tell us that we're focusing on van der Waals intermolecular forces in part A. It says chlorine has a low boiling point because the forces between the molecules are weak. So what we need to be able to deduce is that chlorine is a diatomic molecule, Cl2. So chlorine atom sharing a pair of electrons with another chlorine atom like that, that is a non-polar covalent bond, and therefore the only type of intermolecular forces there will be between the molecules are van der Waals forces. So that's the first thing that we need to be able to deduce. If we were to have polar bonds, then we would need to consider whether there were permanent dipole-dipole forces between the molecules, which would depend on the shape of the molecule and any symmetry that there might be, or whether there might be hydrogen bonds between the molecules. And even though we call them hydrogen bonds, they are intermolecular forces. I know, big pet peeve of mine. So, how do van der Waals intermolecular forces arise between molecules of chlorine? Now, the van der Waals forces are all to do with the movement of electrons within either an atom or within the atoms in a molecule. So the difference between van der Waals and our permanent dipole-dipole forces is that the van der Waals forces are temporary. They are not caused by permanent differences in electronegativity between the atoms within a molecule. It is literally the electrons moving within an atom or within a molecule, and those electrons being in a certain place at a certain time, which then creates what we call a dipole, which is when we can assign a partial positive and a partial negative charge to our atom or our molecule to show actually if the majority of the electrons are in this place at this moment in time, then that part of my atom or molecule will be able to be given a delta negative sign because it's going to be partially negative. It's going to be slightly more negative than the other part of the atom or molecule where there are fewer electrons hanging out. And that across that one molecule is then a dipole. So the dipole being the unequal distribution of electrons, and the result of that is our partial charges. Then, when you have an uneven distribution of the electrons in one molecule, that's then going to affect the next one, because if we've got all of my electrons, say, on this edge of the molecule, then in my next molecule here, to the right of the pen, the electrons in this molecule are then going to get repelled by the ones here that are all pressed up on this right hand side of this molecule, and these electrons are then going to get repelled away, which then generates partial charges in that molecule as well. And the phrase we use for that is we say that the first molecule induces a dipole in this second molecule. And it does that by repelling the electrons in this molecule to one side, and then we can assign partial charges there as well, and that will have a knock-on effect on the next molecule and the next and the next, until obviously the electrons move. And electrons are constantly moving, which is why these forces are temporary. They're also instantaneous. They don't last, you know, forever. It's not constantly there, unlike a permanent dipole-dipole force or a hydrogen bond. As soon as those electrons move, we'll then get a new dipole existing in molecule 1. That will then induce a new dipole in molecule 2. And then again, the electrons will move, and then we'll get the same thing happening over and over again. Now, there are different words we can use instead of van der Waals intermolecular forces, including temporary dipole-dipole forces, or instantaneous dipole-dipole forces, or London forces. There's a lot of variation. Certainly, for those of you studying AQA, I would go with van der Waals intermolecular forces, or van der Waals forces between the molecules. Now, I know they've said in the question here between molecules of chlorine, but they are quite picky in mark schemes. Even if you say van der Waals forces, they'll often want you to say van der Waals intermolecular forces or van der Waals forces between the molecules. So always let the examiner know that van der Waals forces are intermolecular or between the molecules, because that's often underlined in the mark scheme, so it's non-negotiable. So how am I now going to put that into a 3-mark answer? Well, I think the first thing I'm probably going to need to do is identify that the forces I'm talking about are van der Waals intermolecular forces. So van der Waals intermolecular forces exist between molecules of chlorine. And then we can start to think about what's going to happen within the first molecule, or an individual molecule. So the electrons within a molecule are constantly moving, which creates a dipole. And then I'm going to put in brackets, and this is perhaps more for your guys' context, is that when we think about the dipole across the molecule, we can then assign our partial negative and partial positive charge. So I'll put delta positive region and a delta negative region. Then this induces a dipole in a neighbouring molecule, i.e. if all your electrons are on one side, that's then going to repel the electrons in this one away from it, so then there'll be a delta positive and a delta negative region in that one as well. But then it's really important for us to state what the attraction is between, and it will be between the delta negative region of one molecule and the delta positive region of another. Okay, so that's going to be my final bullet point. So the delta negative region of one molecule attracts the delta positive region in another, and that attraction is the van der Waals intermolecular force that we're talking about. Okay, And that's how I'd answer that. So we've got to be able to identify that those are the intermolecular forces we're talking about. We've then got to be able to explain in words how Van der Waals forces arise. And this isn't a very common question, you might be pleased to hear, but it is really important that we are able to kind of explain each type of intermolecular force. So make sure that you can also explain the permanent dipole-dipole forces that arise between certain molecules, or the hydrogen bonds that arise between certain molecules, because I've seen those as wordy questions as well. So I thought that one was really important to do. Onto the equations, and we need to know a couple of equations for how chlorine reacts with different things. So we've got the reaction of chlorine with water, and then we've got to also know why chlorine gets added to drinking water. And then we've also got the reaction of chlorine with cold aqueous sodium hydroxide, and that's to manufacture bleach. And again, we've got to give an equation for that. There is a third one, which is the reaction of chlorine with water in sunlight. So thinking about how the sunlight will affect the chlorine levels in an outdoor swimming pool, for example. Now, when it comes to these equations, we do need to learn them, like I say. So chlorine, Cl2 plus H2O gives HClO and HCl. Now, sometimes they will link these equations to redox reactions, and you might have to use oxidation states to show how this reaction is a redox reaction. Now, the chlorine, which initially as an element has an oxidation state of 0, appears in both products, and in each product it has a different oxidation state. So in HCl, the H is +1, Cl is -1, so we're going from 0 to -1. And in the HClO, the O is -2, the H is +1, so the chlorine also has to be +1. So the chlorine will go from 0 to +1, which is oxidation, because it's an increase in oxidation state, and 0 to -1, which is reduction, because of a decrease in oxidation state. So that is a redox equation, just in case you get something like that, because they have done that before. Why is chlorine added to drinking water? Because the chlorine kills bacteria, microorganisms, makes the water safe to drink, it sterilises it, something along those lines. Will do the job. Now, chlorine itself is toxic, so we do need to be careful of the levels of chlorine that we add, but a small amount of chlorine is overall beneficial because of its ability to kill microorganisms, bacteria, pathogens, and make the water safe for drinking. Okay. Again, we've got to give another equation for this reaction. Now, the good thing here is we get mimicking of the equation above. So no, we're not reacting chlorine with water in this case, we're reacting it with sodium hydroxide, but we get the same two ions being formed. We're going to get a chloride ion, and we're going to get this ClO- ion, which is our chlorate ion. But we're going to get it with the sodium this time. So we're going to have NaClO instead of HClO, and that's the active ingredient in our bleach. We're going to get NaCl instead of HCl, and then we're also going to make water in this particular reaction. And we also need to remember to balance our sodium hydroxides by adding the 2 there, because we've got 2 sodiums and we've got 2 oxygens and we've got 2 hydrogens. So that would be our equation. So whenever there's something to rote learn, of course, there will be some part of it that literally involves sitting down and rote learning it and writing it out many times until you can do it. But there are similarities between the two, including the 2 ions that we form here and here, and also the redox element. So again, the Cl is going from 0 in its oxidation state as an element to -1, but also +1. So this is also an example of a redox equation as well. hopefully that's been useful. But any questions at all, please do not hesitate to ask. If anyone has any similar questions that they would like me to have a go at, or yeah, any questions at all that you would like help with, please do reach out however you feel comfortable to do so, because I'm always more than happy to help. Thanks so much, guys, and I continue to give you all my best wishes for your revision over the next few days. Take care.